Welcome to this illustration for the preparation of buffer solutions. We'll be using nitrous acid here and its conjugate base pair, which is nitrite ion. Nitrous acid is a weak acid. It ionizes partially in water to produce nitrite ion, its conjugate base pair. So we need to place the label here. Nitrous acid, remember, it's a weak acid. It ionizes partially, that's why we have a double arrow here. Actually, the arrow pointing to the left should be longer. Emphasize the fact that it ionizes partially. Only a small amount of products are formed. Also keep in mind that we are using here the Bronsted-Lowry definition. We have the weak acid reacting with water. Water acts as a base. Water can act as an acid if we place a base. Water as a base will have a conjugate acid pair, which is hydronium. So keep in mind the name of the species here: nitrous acid, water, hydronium, nitrite ion. Also, the additional information that we need to know about nitrous acid, if you look at the table for equilibrium constants, the equilibrium constant value for nitrous acid is 4.5 times 10 raised to negative 4. This is also known as the ionization constant for the weak acid. Generally, it's called equilibrium constant. And we also need to use the equilibrium constant expression. We will be using that a lot in this illustration. So based on this chemical equation that is occurring in water, we only consider the substances that are dissolved, which are in aqueous form, and not water, which is in liquid form. In our equilibrium constant, it has an activity of 1, so it's not considered. It's not part of our equilibrium constant expression. Here, we only consider those that are in aqueous form. So in our equilibrium constant expression, we consider the concentration of these three species in mole per liter. We actually have exponents here, which are the coefficients placed here in this balanced chemical equation. This is already balanced. Luckily, our balanced chemical equation here has coefficients of 1. For this illustration, we'll be working on this table. These are the givens for this problem, for this illustration. We will first work on knowing the pH when we have 0.5 mole per liter of nitrous acid solution. What will be the pH? Now, the buffer solution will be made up of nitrous acid and sodium nitrite. Buffer solutions would have considerable concentration of both the acid and the base for the conjugate acid-base pair. So using nitrous acid alone, we won't be able to produce a buffer solution because nitrous acid ionizes slightly, so we have a small concentration of the nitrite ion and a larger concentration of the nitrous acid. But once we place the sodium nitrite salt, we will be increasing the concentration of our nitrite, and we will have both of this in considerable amount, higher amount, and in such a way that we already have a solution that will act as a buffer solution, wherein once we place a base in this buffer solution, it will react to our nitrous acid. Once we place an acid, it will react with our base, nitrite ion. So that is the buffer solution that we will create. It will have considerable amounts of both the nitrous acid and its conjugate base pair. And then, how do we test the effectiveness of our buffer solution? Since our buffer solution will be acidic, a pH of less than 7, we will determine that later. We will be testing the effectiveness of our buffer solution by placing a base, and we will be using sodium hydroxide here in a small concentration, only 0.1. But first, in this particular row, we will determine what will be the pH if we only have 0.1 mole per liter concentration of sodium hydroxide. It's going to be high. You will see it later. And then after that, we will be placing sodium hydroxide in our buffer solution, which is shown here at the last row. You will see that the pH change is very slight. Alright, so with that, let's start with our problem solving. Alright, so for the nitrous acid solution, we will have 0.5 mole per liter of nitrous acid. And then water, we won't be filling up this column because in our expression here, water is not included. Hydronium ion is actually present, but we will consider this to be approximately 0. Hydronium ion will be coming from the auto-ionization of water, which is written here. Water ionizes to produce hydronium ion and hydroxide ion. The equilibrium constant expression for this reversible reaction is only going to consider those that are dissolved, which are hydronium and hydroxide. So this is at neutral pH at the start. Equal amounts of hydronium and hydroxide ions are produced. Alright? At 25 degrees Celsius, it is found that the product of the concentration of hydronium and hydroxide is equal to a very small value. The product of the concentration of hydronium and hydroxide is 1.0 times 10 raised to negative 14. I hope you can see that. Let's see, to determine the concentration of that, we can use a variable. Since both of these are equal, although they are different substances, let's replace this by n. Let's replace this by n. This is basically n squared, equal to 1.0 times 10 raised to negative 14. If we solve for n, that is the concentration of hydronium and hydroxide as well. The value of n is also a very small value here, 1.0 times 10 raised to negative 7. So this is a very small value. That's why we will place approximately 0 here. For our nitrite ion, at the start, we don't have nitrite ion. This is an incomplete reaction. Nitrous acid ionizes to a slight extent. We will use a variable here, x, to take into account that slight ionization. At equilibrium, 0.5 nitrous acid at the start, slight ionization minus x, slight ionization, production of hydronium, slight ionization, production of nitrite ion. And these are the concentrations of hydronium, nitrite, nitrous acid. We will be placing these values in our equilibrium constant expression. It's going to be x here, another x, and then 0.5 minus x. We'll be writing it down here. So don't forget that Ka is equal to 4.5 times 10 raised to negative 4. X squared, like we place here, x times x, 0.5 over 0.5 minus x. So you will be dealing here with the quadratic equation. I hope you can solve this by yourself. You just have to transpose 0.5 minus x to the other side. You can also solve this using shift solve if you're using a calculator, if that feature is available in your calculator. If you're gonna do that, place an initial value of less than 0.5. That will help you get a positive value. Now, if you solve for x, x is going to be the concentration of hydronium ion, and also, in this case, is also going to be the concentration of the nitrite ion. And x here is equal to 0.0148 mole per liter. Right. What will be the pH? The formula for obtaining the pH is simply negative log base 10 of the concentration of hydronium ion. So in this case, we just place this value inside. The value of the pH here that you will get is 1.83. The pH, if you have a 0.5 mole per liter concentration of nitrous acid, is 1.83. Alright, 1.83. Now let's move on to the next row. What will happen after this? What will happen if we place 0.5 mole per liter of sodium nitrite? So let's say we place 0.5 mole of the salt sodium nitrite to our liter of nitrous acid solution. Sodium nitrite is a soluble salt. I encourage you to look at the solubility table for salts. So if you place 0.5 of sodium nitrite, all of it will ionize to produce its component cations and anions. Alright, so I'm going to place the initial value, start, reaction, and then final. Of course, we have 0.5 here, we have 0 at the start. Soluble salt, all of it will dissolve to produce the component cation and anion, so that after placing it to the solution, we don't have the solid salt anymore, we have the dissolved species. The effect of this is that you added more nitrite ion to the solution that already has nitrite ion. So instead of having 0 here, this will be replaced by 0.5. And in effect, that will shift our equilibrium slightly pushing it towards the left. Don't get me wrong, even though we place nitrite here, this equation won't adjust because sodium nitrite is a soluble salt, especially we're dealing here with very small concentrations, less than 1 mole per liter. So here, in dilute solutions, this is a single arrow pointing to the right, complete reaction. The second reaction here will give way to the addition of the nitrite ion. So we will add 0.5 here, we will have a new equilibrium. So with that, we will be using another variable. Just remember the initial value that we place here. Whatever happens to our equilibrium, we place the original value, and the new variable that we place here will account for the new change in equilibrium, the shift in equilibrium for this system. Alright, so now we have 0.5 nitrite ion at the start. So hydronium is still approximately 0. We're now using a different variable to account for the new shift in equilibrium. The same thing, you will place these values to our equilibrium constant expression. We will be solving for y, right? So I leave this to you guys. The value of y is also the concentration of hydronium in this new equilibrium. The value of y is the pH of the buffer solution is 3.35. The next part of this video is about buffering action. What will happen if you place sodium hydroxide, 0.1 mole of sodium hydroxide to a liter of this buffer solution? Keep in mind that sodium hydroxide is a strong base. I feel the need to emphasize that it is a strong base by showing to you what will be the pH if we only have 0.1 mole per liter of sodium hydroxide. Sodium hydroxide, a strong base, it is completely dissociated, especially at a very low amount, such as 0.1 mole per liter. So if we have 0.1 at the start, completely producing its component cation and an ion. So we have 0.1 of sodium and then 0.1 of the hydroxide. Remember the auto-ionization of water? Water produces hydronium and hydroxide. The addition of the hydroxide will shift that equilibrium. You remember I wrote this earlier. So this is times 10 raised to negative 14. And then here we don't know the concentration of hydronium, but here we place 0.1. So it's going to be 0.1 plus 1.0 times 10 raised to negative 7, but we won't consider that. It's a very small value. So here, this will give us immediately the concentration of the hydronium, which is 1.0 times 10 raised to negative 13. Then we can place this to our pH formula. Then we will get a pH of 13. The pH of a solution with 0.1 mole per liter sodium hydroxide is very high, it's 13. Now if we place sodium hydroxide to our buffer solution, there will first be an acid-base reaction. Right? This is the acid, this is the base. So there's going to be an acid-base reaction. I'm going to write it down here. Acid-base reaction. And in an acid-base reaction, water is produced and also a salt is produced. This is going to give us the same effect as writing the whole formula for the acid and then the base. Right? Acid-base produces water and the salt. What will happen is, once you form the salt, just like before, sodium nitrite is a soluble salt. It will produce sodium and nitrite. Okay, so we will use this. So at the start, we have 0.5 mole per liter of the nitrous acid. And then we have 0.1 of sodium hydroxide. So start, reaction, all of the base will be used up. Okay, so keep in mind that we also have a salt at the start, 0.5. So here, all of the sodium hydroxide that we place here will be used up. And then it will consume some of the acid. Then after that, this is the reactants. Products will be produce. Of course, there's a lot of water present at the start, but the but the main focus here is the amount of salt that is added. From 0.5, we now have 0.6. Alright, so at the final concentration here, our nitrous acid from 0.5 is now reduced to 0.4. We will be placing that here. Our salt from 0.5 will now be 0.6. And then, once it is formed, of course, it's just 0.6 here. Just going to be 0.6 there. That's why this equation that I wrote here also works. So now it's going to be 0.6 at the start. This is still approximately 0. Now we will be working with a new shift in equilibrium. We will be using a new variable to account for the new change in the equilibrium for this system. Okay, so initial 0.4. Why? Because some of it was used up in an acid-base reaction. Because we added a base, the acid that we have now, the nitrous acid, is lesser than the original. So it's 0.4 now. The equilibrium will be 0.4 minus Z. Z will account for the new shift in equilibrium. Nitrite ion, the amount of nitrite present here is more than before as a result of the acid-base reaction, because in an acid-base reaction, salt is produced. We will be solving for Z. This is another quadratic equation. Z is going to be 2.996 times 10 raised to negative 4 mole per liter. The value of Z is also the value of the hydronium ion. So here, even if you add 1.0 times 10 raised to negative 7, the initial value of hydronium, it will have less effect to our computation of pH. All you have to do here is to plug in the value of Z. The pH that you will get is, alright, 3.52. Alright, 3.52. That is the increase in pH after placing the strong base to our buffer solution. 3.52 minus 3.35, that is 0.17, a very slight change. We have an effective buffer solution here that was able to control the increase in pH. Instead of 13, which is very high, very basic, here the pH increased to a slight extent. That's how buffer solutions work. To summarize that, buffer solutions contain considerable amount of the conjugate acid-base pair, and it's done by placing a salt that produces the other pair. So for this one, we have an acid-base conjugate base, a salt that produces the conjugate base for this acid. Another variation of this is when we use a base instead at the start, and then we have a salt that produces the conjugate acid for that base. Right, so that is another variation. Alright, so I hope you learned something in this video. Please subscribe to my channel. Please like this video. Support for more STEM and chemistry related content. Thank you.